Hey everyone, welcome to my review session on the absolutely epic history behind the laws of motion. I am your professor for today's explainer, and we have a really fantastic journey ahead of us. Whether you're actively prepping for a massive physics exam, or you honestly just want to understand the invisible rules that govern literally every single movement in our universe, you are in exactly the right place. So grab your notes, get comfortable, because we're going to break down these major concepts step by step. Here's our game plan for today. We'll hit 1. The evolution of motion. 2. Galileo's rebellious inclined planes. 3. The first law, inertia and equilibrium. 4. The second law, force and momentum. 5. The third law, action and reaction. And finally, 6. Your ultimate study guide. Let's just dive right in. All right, kicking things off with section 1, the evolution of motion. Now take a look at this timeline. It's fascinating because it maps our whole journey from the ancient Greeks and early Indian concepts right up to classical physics. For centuries, the Greek philosopher Aristotle basically dominated scientific thought. But concurrently, ancient Indian thinkers were developing this incredibly elaborate system of ideas on motion. They explored this concept called vega, which was essentially this persistent tendency of an object to move in a straight line. It astonishingly parallels our modern concept of inertia. Furthermore, the Indian mathematician Bhaskara actually anticipated the modern notion of instantaneous velocity using early concepts of differential calculus. It was this incredibly rich tapestry of thought long before Galileo and Newton ever arrived on the scene. So, what did Aristotle actually get wrong? While Aristotle thought uniform motion required a constant push, he completely missed the invisible force of friction that Newton later accounted for. Think about it. If a kid pushes a toy car across the living room floor, it eventually stops when they let go, right? Aristotle looked at that and said, aha, you clearly need force to keep it moving, but he was totally fooled by terrestrial friction. If you literally removed the friction of the floor, that little toy car would keep going forever without any extra pushing. Force doesn't maintain uniform motion, it only changes it. Moving right along to section 2, Galileo's rebellious inclined planes. This right here is the definitive mythbuster moment in science. Step by step, Galileo's double inclined plane experiment basically proved that on a frictionless horizontal plane, a ball's motion would never cease. This firmly established the concept of inertia. Look at the visual mechanics of this setup. When a ball rolls down one slope, it obviously gains speed, and then it rolls up the facing slope to almost its exact starting height. Galileo brilliantly reasoned, well, what if we lower the angle of the second slope? The ball has to roll further to reach that exact same height. And then here's the kicker. What if we make that second plane perfectly flat? The ball will just roll infinitely, forever trying to reach a height it literally can never attain. Mind-blowing, right? Okay, section 3. First law, inertia and equilibrium. Let's track the logical flow here. If no net force acts on an object, its state of motion simply resists change. This is the bedrock definition of inertia. Every body continues in its state of rest or of uniform motion in a straight line unless it is compelled by some external force to act otherwise. Picture a spaceship. If a spaceship turns off its rockets in the deep, empty vacuum of interstellar space, it doesn't just stop. No way. It coasts at that exact same velocity forever. Now check out these free body diagrams. By visualizing these forces, we firmly separate the idea of equilibrium, where opposing forces perfectly cancel out, from non-uniform motion, where a net external force actually drives acceleration. Look at the book on the left. Gravity is pulling it down, sure, but the table pushes back up with a normal force. These perfectly cancel out to zero. That right there is equilibrium. Now look at the car on the right picking up speed. There is a net external force, in this case the friction between the tires and the road, actively pushing the car forward. Because the forces do not cancel, the car accelerates. If you want to crush your exam problems, you've got to nail these two definitions. You must understand velocity as a constant state, and acceleration as an active change in that state. Velocity is simply how fast you're going in a specific direction. If your velocity isn't changing, your acceleration is zero. Period. Acceleration only happens when a net external force actually kicks in, speeding you up, slowing you down, or changing your direction. Which brings us perfectly to section 4, second law, force and momentum. Before we can even touch the math of force, we have to talk about momentum. It's a vital vector quantity that scales with both how heavy an object is and how fast it moves. Imagine a fully loaded truck and a small bicycle cruising down the street at the exact same speed. Which one is harder to stop? The truck, obviously, because it has way more mass. Now imagine two identical bullets, but one is just tossed by hand and the other is fired from a rifle. The much faster one does the damage. Momentum captures both of these realities perfectly. Mass times velocity. Let's put this on the field with a visceral, real-world application. Both of these players are catching the exact same cricket ball with the exact same mass and the exact same incoming velocity. So why does the novice get absolutely bruised hands while the pro barely even flinches? The secret lies entirely in the second law of motion. The mathematical relationship here shows that force depends on how fast momentum changes. F equals dp over dt. What this means in plain English is that drawing your hands back to increase the time of the catch mathematically decreases the stinging force. The novice holds their hands totally stiff, stopping the ball instantly. A tiny dt, or a tiny change in time, results in a massive, painful force. The seasoned player naturally pulls their hands back, increasing the time it takes to stop the ball. A larger time interval means a much smaller, safer force. And this perfectly explains impulsive forces, like a batsman crocking a ball straight back down the pitch to rapidly reverse its momentum. When that bat hits the ball, they are only in contact for a fraction of a millisecond. It's literally almost impossible to measure the exact force or the exact time interval separately. But because we know the change of momentum, the ball was coming in at one speed and leaves at another, we can easily calculate the impulse. Impulsive forces are just regular forces, they just act incredibly fast. All right, almost there. Section 5, third law, action and reaction. Listen up because this brilliantly illustrates the absolute biggest misconception I see from students. Because action and reaction act on two entirely different bodies. They never, ever cancel each other out. This is so vital for your exams. When you walk, your foot pushes backward on the ground, that's the action. The ground pushes forward on your foot, that's the reaction. If they acted on the same body, they'd cancel out to zero and you could literally never move. Let's look at these diagrams side by side to really hammer this home. Bouncing billiard balls show true action-reaction pairs, whereas arresting book's forces simply represent static equilibrium. Let's be perfectly clear on this. The book on the table experiences gravity pulling it down and normal force pushing it up. Those cancel out because they act on the exact same object, the book. But a true action-reaction pair would be the earth pulling the book down and the book pulling the earth up. They are equal, opposite, and act on entirely different bodies. Finally, Section 6, your ultimate study guide. Go ahead and take a screenshot of this table because it is literally your ultimate cheat sheet. It cleanly contrasts Newton's 3 laws with the everyday practical examples you are for sure going to see on the test. The first law is all about inertia, like when your bus stops suddenly, but your body wants to keep moving forward. The second law is the math of momentum, why cars accelerate and why cricketers pull their hands back. And the third law is the law of pairs, billiard balls striking each other and bouncing away with equal and opposite force. Keep this quick reference list of key definitions handy for your exam prep too. Remember that equilibrium relies on forces perfectly canceling each other out. And definitely don't forget friction. It's that sneaky contact force that completely fooled Aristotle for over 2 millennia. It always opposes relative motion between two surfaces. I'm going to leave you with this provocative historical thought to chew on long after this review session concludes. We've seen how brilliant minds from ancient India to Renaissance Italy built upon and sometimes totally shattered the ideas of the past. Keep questioning everything you see around you. Best of luck on your physics exams, stay curious, and I'll catch you in the next explainer.